use it for the good of each and every one of us. Um, just give it a moment. We see what is happening with technology. Technology is there to serve us. Yeah, so the topic, if we could start from the first slide, the topic, first slide. Yeah, so as an introduction, we are looking at the growing demand for energy. Oops, don't know what's happening. Can I share? Yeah, the topic is photovoltaic. I mean, the title is photovoltaic systems, and if we could hold that as an introduction so that we don't flip so much. I was saying there's a growing demand of energy, which has forced researchers to look for alternative sources of energy. And among these cheap sources of energy is photovoltaics. The International Energy Agency has noted a declining prices of photovoltaics, and it estimates that solar systems in general will have to supply about 5% of the global electricity consumption by the year 2030. These estimates are likely to rise to 16% by 2050. My slide is getting out. I don't know what's the problem. There's a lot of fluctuation. Go back the second slide. Mm-hmm. So that the second slide, you seem to have lost it. That's the third slide.
Prof, can we try screen sharing from your end?
From my end, because this other side is becoming difficult.
Yes, kindly go to that button that is green, share screen.
Sharing.
Yes, share screen.
Yeah.
And then you can screen share. Can we try screen sharing from your end? Yes. Kindly go to that button. The green one. Share screen. Yes, share screen.
It's saying stop sharing. So have you stopped sharing?
Just yes.
You are sharing, Prof. You need to put the presentation, please. Yes.
Go online. So the present that not in the screen. If I go to Windows. Have you stopped sharing?
I am not currently sharing. Yes.
So it is just a minute.
in the meantime, Dr. Rebecca, we can also try to convert the PPT into PDF. Probably it's the net. Thank you, Dr. Rebecca.
Have you been able to share? Yeah, thank you. Now we can see your screen. Go to the presentation. Thank you. You're sorry about that. You can put it on display mode. No, go to the presentation. The PowerPoint, yes. Prof, you can proceed. You can unmute yourself. We can't hear you. Yeah, thank you.
So I was saying the topic, the subject is photovoltaic systems, and under that we are looking at solar solutions for the future. We have done this work with Timona Soita, who is a member of department in our Department of Physics. So this is the book we have ordered as far as photovoltaic systems are concerned, and it has 8 chapters. At the moment, we are using Lambert as the publisher, who the cost of the book is about 10,000 or 87 euros. I was saying there is a growing demand of energy, which has forced researchers or scientists to look for cheap alternative sources. Among these cheap alternative sources, we have photovoltaics as one of them. From the International Energy Agency, in short, IEA, has noted a declining prices of photovoltaics and estimates the solar systems in general to supply 5% of the global electricity consumption in the year 2030. These estimates are likely to rise to 16% by the year 2050. This can only be achieved by increasing the global production of solar energy to about 4,600 gigawatts by 2050. At the same time, solar and wind energy is expected to contribute to up to 50% of the total energy generated. So reduced costs of energy generation and improvements in performance will lead to more penetration of solar energy across the globe. This, coupled with more research, will make solar energy cheaper than the fossil fuels, which is not abundant or which is becoming very expensive every day. So using innovative new designs, researchers are continuously working to improve photovoltaic energy systems. This work is geared towards reducing the power generation cost by combining several materials in photovoltaic cells. The best efficiency of 39.2% has been demonstrated from multi-junction solar cells. However, it should be observed that this is applied in space technologies that have complex fabrication processes. Currently, the theoretical efficiency of crystalline silicon-based solar cell is approximately 26.7%, and for thin film technology is about 23.4%. These solar cell technologies outlined above are mature, already in production. However, the complexity of the production process and the energy consumption needs to be reduced. Currently, inexpensive and easy to fabricate solar cells are under investigation by researchers, and most of these solar cells technologies are categorized as emerging PV technologies. Examples include organic solar cells, dye-sensitized solar cells, quantum dot solar cells, peroxide solar cells. In short, PSC. PSC shows very promising results and can be favorably compete with crystalline silicon solar cells in terms of efficiency. Peroxides were discovered in Ural Mountains in Russia by a German scientist, and basically describes the compounds having crystal structures like calcium titanium oxide. The materials being used for newly developed peroxide solar cells have their structural form of ABX. They are like ABX. A and B are cations, and X is a bonding anion. In comparison with traditional silicon solar cells, PSC absorbs sunlight with 100 times thinner active layer. These are thin film kind of material. This ABX structure allows for variation in the energy cap by mixing and matching scenarios where we can have multiple compounds by substituting any of the constituents. And within a decade of its inception, PSC has already overtaken thin film technology, such as cadmium telluride or copper indium gallium selenide, and reached the level of crystalline silicon solar cells in terms of efficiency. Already an efficiency of 25.2% for silicon junction PSC has been realized by a team led by Michael Saliba at KRICT, where the theoretical efficiency for this PSC is about 31%. From a diagrammatical perspective, you can see that we have on the y-axis the efficiency and the band cap, identifying materials, the semiconductor materials, and you can see there is a peak where there is silicon and gallium arsenide, and then there is the peroxide I'm talking about, which is having a band cap of 1.7 electron volts. There's maximum conversion efficiency independence with a band cap associated with the semiconductors. So silicon and peroxide are almost in the same range if the materials are arranged in a certain way. So we note that when peroxide cells is in tandem with other solar cell technologies, they are giving varying efficiencies. Because you can, peroxide has a material that changes its energy cap. You can vary the energy cap and get different structures. And that's a big advantage with peroxide. Peroxide and CIGS, or thin film technology, tandem cell has shown efficiencies up to 21%, whereas when combined with crystalline silicon technology, the peroxide silicon tandem cell has shown efficiencies up to 28%. That shows better performance in comparison with a single PN junction silicon and also a single junction of peroxide solar cell cells. The efficiency of peroxide crystalline silicon tandem solar cells are in the range of 32%, 32.8%, which is within the gallium indium phosphide or gallium arsenide tantalum solar cells that are used in outer space. This type of solar cells are realized through intensified processes and expensive manufacturing techniques. With more research, the efficiency of the peroxide and silicon tantalum cell can get towards 30%. Although PV technology or photovoltaic technology is not the most widely used energy source due to the low energy conversion efficiency and high initial system cost, in comparison to non-renewable energy sources, it is a fast-growing energy source in the power sector. So far, solar modules from crystalline silicon single-junction solar cells have their conversion efficiencies in the lab as 26.3%, while the upper theoretical energy conversion efficiency of solar cells with a band gap of 1.14 e.g. silicon. And from the diagram, you can see the emerging PV solar cells. In this case, we are looking at the labs or where they are being manufactured. You can see that from 1985, amorphous silicon single layer came into existence. We have amorphous silicon solar cells. It has progressed, but it's like it's plateauing. It's not improving from 2010. In the same vein, we have dye-sensitized solar cells, which started in 1990, but it's kind of plateauing from 2010. And we have also the smaller area organic PV systems, which has also progressed, but it's not the progression when you compare with the last one, peroxide. Peroxide has a very steep rise in conversion efficiency progression. So we note that multi-junction solar cell approach has been used to increase theoretical limits of single junction solar cells. It has been shown that series connection of tantalum solar cells can reach conversion efficiencies in excess of 40% if proper material combination is selected for the top and the bottom solar cell. Higher than 40% can be attained if the relationship of the cell is where the energy gap for the top cell is related with the bottom through that equation, where half of the energy gap plus 1.14 electron volt, where EG and EG top and EG bottom are the band gaps of the top and the bottom diodes respectively. This equation holds true when the bottom cell band gap is between 0.85 to 1.2 electron volts, and hence several material combinations can be identified. One of the materials suitable as the bottom cell is crystalline silicon with a band gap of 1.14 electron volt. This has led to many activities focusing on the development of a tantalum solar cell using a crystalline silicon bottom solar cell. With crystalline silicon bottom cell, the highest conversion efficiency being achieved when the top is about 1.7. When combining well-established crystalline silicon solar cell technology with other material systems of application processes, a number of crucial aspects must be considered. Although we know amorphous silicon has a favorable band gap of 1.7 electron volt, its tail states hinder it in being applied on the formation of tantalum cell with high values of open circuit voltage. This is a condition for attaining high efficiency in a tantalum structure. Also, silicon oxide and crystalline silicon-based quantum dot and quantum well have been researched for the top solar cell material. And successfully, the two materials have shown comparatively low conversion efficiency. Although compound semiconductors have been researched as potential top solar cell absorber material, high fabrication temperatures, the lattice mismatch between silicon and the compound semiconductor, the fabrication costs are the biggest hindrance to its application. In the last decade, the peroxide material system has attracted a lot of research, either for single junction solar cell or as a material for peroxide silicon tantalum solar cells. These are shown high energy conversion efficiencies with open circuit close to the theoretical limits of silicon material, and in addition, a variety of deposition methods at low temperatures can be used in the application of peroxide top cell solar cell on a crystalline bottom solar cell. A conversion efficiency of about 20 has been realized with peroxide single junction solar cells. So the peroxide silicon tantalum solar cell has both high and low bandgap material in a single device, enabling the device to be active in both long and short wavelength regions of the electromagnetic spectrum, where each wavelength region can effectively be converted to electric power, resulting in high efficiencies. As a peroxide solar cell, it has unique properties like high absorption coefficient, variable bandgap, high defect tolerance, high open circuit voltage, abundant availability of its constituent element, and ease processability. Peroxide
I didn't understand that.
Peroxide silicon can use high energy, can use the high energy blue and green light, which is more efficient than silicon. And we note that peroxide tantalum solar cell with high efficiencies is only possible if the peroxide top cell and the silicon bottom cell operate at very near to their theoretical limit. It is worth noting that peroxide silicon tantalum solar cells with satisfied energy conversion efficiencies of about 27% have been achieved. This realization of solar cells with high energy conversion efficiencies approaching or even exceeding 30 is visible in the near future. So maybe before we think of which kind of materials we are going to use, let's remind ourselves of what is this photovoltaic cells? What are these photovoltaic cells? We note that a solar cell is an electrical device which converts energy of sunlight directly into electricity by the photovoltaic effect, which is a physical and a chemical phenomenon. The solar cell structures consist of either a PN junction or a PIN junction. Initially, the instant radiation directed on the surface are absorbed, resulting in a creation of electron hole pairs. Then these photo-generated electron hole pairs are separated by the electric field and subsequently collected at the terminals. The charge collection of the photo-generated charges occurs due to diffusion or drift or combination of both transport process to the conduct of the solar cell. The figure in the next slide shows the kind of structure I'm talking about. Like in A is a homo junction. Homo means we are using the same material. It is crystalline silicon, so it is only crystalline silicon we are using. In B, we have a heterojunction, meaning we are using two different materials. This is amorphous silicon and crystalline silicon. And C, we are having homojunction of amorphous silicon alone. You can see it is in the range of 1.7 electron volt, which is in the, good for absorbing the blue or green part of the spectrum. And then D, we are having a structure where it's now only peroxide, but peroxide has a whole transporting section and the electron transporting section, and then, of course, the metal back conducts and the front conducts in that manner. And finally, what I've been talking about is E, where we are having a tandem solar cell. In this case, we initially have crystalline silicon, which is the red, and then peroxide, which is blue. And it's done purposely because it absorbs the light in that wavelength region. So I've described the diagrams where we have talked of the silicon homojunction, which is absorbing, it's assumed that absorption of high energy photons is done in the whole of the PN junction. The electron hole pairs that are produced are predominantly transferred by charge diffusion for that homojunction. Heterojunction solar cells that consist of a crystalline silicon absorber and amorphous silicon conduct layer is shown in B, and the heterojunction structure, when compared with traditional homojunction solar cells, there is a minimization of optical loss, particularly in the emitter or in the upper zone of that structure. As a result, we have a higher short circuit current density and high open voltage, which is an type layers are used to form electrical contacts. The main charge transmission, since it has higher diffusion length. The PIN structure is currently applied in many thin film solar cells. This arrangement, where the intrinsic material is placed between the P-type and the N-type, has an advantage in that it gives a higher voltage. The charge collection process is done by drifting mechanism of the electron hole pairs to the contacts. Yeah. So the next one is how we will determine the current or the voltage in these materials. We get the current, we talk of short circuit current density or open circuit current, open circuit voltage. Short circuit current density is realized when the voltage is 0, while the open circuit voltage is obtained when the current is equal to 0. It will be easier to visualize it if we showed the IV characteristic curves, but for now we assume we know. So the maximum power density output of a typical solar cell is given by the product of the voltage at maximum power point and the current at maximum power point. When we take power is the product of voltage and current. It's a bit technical. So that these two parameters are derived from the current and the voltage characteristics of a solar cell, where the efficiency is as shown in equation 1. And hence the fill factor is calculated by equation 2, and ideal solar cell can be described by equation 3. Where the current and the J naught exponential, we describe the behavior of the current in the solar cell exponentially. From this equation 3, we note that Q is representing the elementary charge, V is applied voltage, K is the Boltzmann constant, T cell is the temperature of the cell, J naught is saturation current density. So that the open circuit voltage of the cell can be determined by VOC with that equation 4. Understanding the fundamental limits in the energy conversion process of solar cells and determining the potential upper limit of the energy conversion is important in developing a high efficiency solar cell. The maximum conversion efficiency is the theoretical energy conversion limit of a semiconductor-based solar cell. In deriving the limit, we shall assume that the solar cell is described by a single junction, which consists of a semiconductor with a constant band gap. We assume we are using a semiconductor with only one band gap. The light beam with photon energy equal or greater than the band gap is absorbed. The behavior in the semiconductor, there is a cap in the energy. When you look at the electrons and the holes in a semiconductor, there is something we call a band gap, and each material is unique with its band gap. The material you grow has its unique band gap. So the absorption only takes place, or the promotion of an electron from a lower state to a higher state only occurs when the energy, which is from the light has energy in the form of photons, has enough energy to raise or overcome that band gap, to overcome that gap that is between the two levels of excitement. When the electron moves from valence to conduction, there is a band gap that is concerned to be that has to be overcome. So here we are saying, in deriving the limit, the light beam with photon energy equal or greater than is absorbed. If it is less, it will not be absorbed, while photons with energy smaller than the band gap are not absorbed. All the photon-generated electron pairs are assumed to be collected at the contacts, meaning there is no loss. What is generated is collected at the terminals. Therefore, the recombination of electron hole pairs is not considered, but only thermalization and absorption losses are taken into account. Thermalization losses occur for energies greater than the band gap, while absorption losses occur for energies less than the band gap. So the absorbed photon flux density of the sun by the solar cell is given by that equation 5. We are assuming the solar cell is at 0 for us to get the maximum limit. We are assuming the solar cell is at 0 degrees Kelvin, and the temperature of the sun is 60,000 Kelvin. So using that, but we know very well when we are on this, when we are on Earth, we are not at 0. When we are on the ground on Earth, we are around 300 degrees Kelvin. Degrees Kelvin. But for assumption to get the maximum limit, we assume that the solar cell is at 0. That's how we can compare when it's at 0 and when it's at on the ground of 300 Kelvin. Then we can know how much, if there are no losses, how much you can get or how much you can convert from the photons that are falling on the cell. Of course, those are the standard symbols. H, C, K, and E, G are Planck's constant, speed of light, Boltzmann constant, energy, band gap for the photovoltaic material, and the photon flux can be approximated by equation 6. We are trying to estimate how much energy you can get from the sun, assuming we are saying the absorption is from the absorption only takes place above the energy cap. So we are starting from the energy cap up to infinity. How much energy can you get, can a solar cell get from the sun? That phi sun is the black body radiation flux from the sun, which is given by equation 7. The photon current density of the solar cell is given by that equation, where we are multiplying the charge and the flux density. The electron output from the power density of the solar cell is calculated by equation 8. We are trying to maximize how much energy you can get from the sun. So from the graph, you can see that on the ground, which is around 27 degrees centigrade or 300 degrees Kelvin, the maximum conversion we can get on a solar cell is 33%, 33.5%. That's dotted blue. And then if you take the temperature of 6,000 Kelvin, which is the temperature of the sun, we can get on a solar cell, we'll get on the ground will be 31.2%. But ultimate efficiency, if we assume that with the difference between the sun and the earth. The sun is at 6,000 K and the earth is at 0 K, then we can get the maximum efficiency conversion, 49 and 43 respectively. So the design, at the moment, the conversions are less than 20%, but with more research and modifications, we can get closer to 33.5 conversion efficiency. So the input from the sun is represented by equation 9. From the above equations 8 and 9, the energy conversion efficiency is determined by the ratio of the two, the power out and the power in. So using the blackboard spectrum of 6,000 K and air mass 1.5 global spectrum, the solar cell gives a maximum conversion of 44% and 49 respectively. 44 when you are taking T of 6,000 K, and 49 when you are taking the air mass 1.5 for a material of a band gap 1.1 electron volts. So theoretically, it is possible to achieve higher efficiency from the tandem solar cell of 31.2 at air mass 1.5 and 44 out of space. When we are looking at the scenario outside the atmosphere. So in conclusion, we are saying peroxide silicon tandem solar cells have a very high potential to reach low-level cost of electricity. To achieve a high efficient and reliable tandem peroxide silicon solar cells, a multi-level approach is required. This includes improving the performance of individual layers in each cell, examining the charge transport in each layer when they are stacked, and finally, efficient light in coupling between the top and the bottom cells. One of the critical conditions for higher device efficiency is proper choice of the band gap for the peroxide top cell in a tandem cell, in a tandem structure. Optical losses due to parasitic absorption losses resulting from both inefficient intermediate reflecting layers and inefficient absorption in the top cell have to be addressed. Low absorption coefficient of silicon bottom cell reduces the light absorption and reflects in the efficiency of the tandem solar cell. Stable and efficient light management is necessary for the further improvement in the device performance. The research on replacing of highly pure, expensive silicon with recycled leftover multicrystalline silicon in tandem cells without much compromise in efficiency will upscale low-cost tandem cells. What we've been talking about is that structure. The upper one is peroxide, the lower one is silicon, and the light beam, which is having from the electromagnetic spectrum, from the green, blue, up to the red, yellow, red. Silicon is good in absorbing the red, yellow, red region or low energy spectrum, and peroxide is good in absorbing high energy spectrum. So when you combine the two, you have a better efficiency. And so silicon heterojunction solar cells still exist as the favorite bottom cell over homojunction cells. Efficient doping with hydrogen persivates and stabilizes silicon and its heterojunction cells. These are some of the aspects considered in the book we published, Photovoltaic Systems. Thank you for your attention.
Thank you very, very much, Prof, for that presentation, very informative. I want to kickstart, I'm seeing time is not on our side. I want to kickstart the Q&A session. And I will start with a question. As a lay person, I am, with the rising costs of Kenya Power, I'm wondering how can I utilize this kind of technology in my household? So I'm sure there are others who have questions. I will give Dr. Mbindio the chance to moderate the session. And anyone who has a question, you can use the chat function. You can also raise your hand, and then we will let you unmute yourself for Prof to give us the answers. You can start with that question.
Yeah,
Thank you.
I'll say for you, at the moment, actually you can install. The installation for these current solar cells of silicon is not very expensive. For a small, consumer like a family of 4 or a family of 5, you need a system of panels and batteries, which will cost you around 200,000 to install, and it will serve you for more than 15 years or 20 years. So it's the initial cost that is prohibiting, but for now, if you have around 200,000, you can install the system, photovoltaic system of silicon solar cells. It is manageable. And some people actually have resorted to that because of the fluctuations in power and KBLC being unreliable.
Thank you.
Mm.
So thank you, Professor, and congratulations on publication of your book. So
Yes.
the other question is, where can we get the book? How can we purchase it over here?
Getting it is not difficult. You just get online and you make the orders. In fact, they were asking how many orders I can be able to get to sell out. So it's not difficult. You go to Lambert online. There's an online access and order.
Thank you.
Mm.
So, questions, please. I can see somebody has raised his hand, but I'm not sure who it is.
Come on.
Hello, Chair. Can I proceed?
Yes, please.
Okay. Thank you so much, Prof, for that presentation.
Thank you.
And congrats for that book.
Yeah.
My concern is, I think you are not so concerned about the Hasras, that it's very expensive. 10,000. How are you able to give us a copy in the library? Please.
For your information, there's already a copy in the library.
Oh, that is then okay. I congratulate you. Thank you.
Yeah.
Thank you so much. It's a good area and a nice book. I was just concerned about the costs, but I can scan the one in the library. Thank you so much.
No, you need to buy.
Thank you. And the professors get the book allowance. They can now buy it.
It's okay. It's okay.
Thank you.
Well, thank you, Prof. Perhaps the other question is for an institution such as ours, Professor Mulati, how can we reduce the bill if you look at where we can actually put in lights for reducing our over-reliance on Kenya Power and Lighting?
Actually, I was very impressed with South Africa. South Africa, just like the way we came up with the laptops for primary schools, it has installed, PV systems in all primary schools, which is a big step forward. And it's an investment which encourages now people to do more research and avoid over-reliance on, KPLC. KPLC is okay, it has served its purpose, but I think it's a time now for us to become more independent by installing these systems in, in primary schools and in the universities even worse. We need to put it, if we put it there, like in, there's this university, In Kenya, we are having installation in Strathmore. Strathmore has put the panels, the electrical, the photovoltaic panels, and it is saving a lot of energy, although it was using the charge to install. But I think in a small way, we can avoid it. It is not difficult. As a system, as a university, as a policy, it's not difficult to realize it.
So thank you, Prof, for that. Any other questions? So as participants think, so what is next for you in this research area? What are you next interested in?
For me?
Yes.
Me, I'll be very happy to see that we take advantage of the free gift which God has given us, free, and we are not using it. And you know, even with the instabilities, political instabilities like what is happening in Ukraine, it is forcing us to think, whether we like it or not, of other alternative sources of survival, because our reliance on fossil fuels is putting us prisoners. So really we need to be free, and for the sustainability aspect, I'll advocate for greener technologies as a solution for the future. So for me, I'm still passionate about alternative energy, especially photovoltaics, and I want to pursue that interest so long as I'm available.
Asante, Prof.
Yeah.
So there being no other questions, may I hand over to Dr. Maina? Thank you.
Thank you very much, Dr. Mbindio, for that session. We really appreciate your time, all those who took their time to be with us this afternoon. We at the Directorate are very grateful and looking forward to hosting another webinar soon. We shall just be on the lookout for our posters. Thank you very much, Professor, for that enlightening topic. And we also look forward now to hosting you for your inaugural public lecture. I think it is coming soon. We'll also advise on the time. Thank you very, very much for your time and your presentation. We have learned a lot, and I'm sure there are students who are in the call and they have also gleaned a lot of wisdom. As we conclude, I'll want to give our director a chance to give his concluding remarks. Thank you very much.
Thank you, Dr. Rebecca, for good coordination. Thank you, Dr. Mbindio. Thank you, everyone. Congrats, Prof. That's not everyday thing, publishing a book. And I think I'll get myself a copy also to join users of the clean energy and to understand. Thank you, everyone. Thank you. Have a good evening.
Good afternoon too. Thank you very much.